In this segment, we're going to cover binomial distribution. It's a specific type of probability distribution, discrete probability distribution, that results from a very peculiar type of experiment. Remember, we said that before, that a variable is an outcome of an experiment. Here we're looking at a very specific experiment called the binomial experiment, and that leads to a variable that would exhibit what we call a binomial probability distribution. So let's see it. So a binomial distribution results from what we call a binomial experiment. So what is it? What's that binomial experiment? It has four characteristics or four aspects. The first one is that it consists of fixed number of trials. We'll talk about what do we mean by trial. A trial can be such a simple action that as flipping a coin or observing an answer on a quiz or anything else. Okay, so it's not a very complicated action. So we have n number of trials, it's fixed. Each trial has only two possible outcomes. Okay, so unlike other experiments where we could observe 7, 8, 3, 4 events, here it's only two, and that's a very important characteristic of binomial experiment. And we will label one as success and the other one as failure. Now here these are not literally a success and failure, right? It's only that our notation. So this is how we denote one observation. We call it a success, and the other one would be a failure. The third aspect is that the probability of a success is known, and we denote it by small p. And of course, because these are only two, then the probability of the failure is the complement, so it's 1 minus p. Now the fourth one, it's also very important, so you have to be very careful before you say that this experiment is really a binomial, because in a binomial experiment the trials are independent. What does it mean? That means the outcome of one trial, okay, does not have any influence on the outcome of any other trial. For example, when you flip a coin and you observe a head or a tail, then when you flip a coin a second time, so this is a second trial, what you observe in the previous flipping does not have anything to do with what you'll observe next and next. So that's why flipping a coin would be considered as a binomial experiment. All right, so let's dig further. Okay. So these properties that we discussed, if the second, third, and fourth are satisfied, we call the trial as a Bernoulli process. We're not going to use it in our course here, but it's just general information for you. Now, we are interested in the variable that results from the experiment, okay? And as we agreed before, we will call the variable by the experiment name. So the variable will be called a binomial variable. And what is it? Remember, it's always very important to define, to have a very clear definition about the variable, because it will make all the difference if we make or if we define a variable in a manner or if we define it in a different manner. All right, so in a binomial experiment, we define the variable as being the number of successes in n trials, right? So, for example, if we're flipping a coin 4 times, what's the first of all, I need to define what's my success. Let's say my success is head, okay? It can be the tail, doesn't matter. So let's say it's the head. Now, in a 4 trials, how many times I would end up observing a head? It's either 0, okay, not in any one of the trial I could observe it, or 1, or 2, or 3, or 4. So you see now, this x can take 5 values, 0, 1, 2, 3, and 4, because this is how we defined x. and this x we call it the binomial random variable. So other examples than flipping a coin, for example, drawing a card, okay, and let's say we need to we are interested to see whether we're going to observe 5 clubs, okay, so this will be the number of successes. Or when voters go and vote, and or they are just telling their intention to vote. Are they going to vote for a Democratic or Republican candidate? Okay, see, so here we have only two possibilities, either Democratic or Republican. So this will fall under a binomial experiment. All right. Okay, so as I mentioned earlier in the flipping coin example, I said that the variable that we defined it in that example, that it's being the number of heads observed after flipping the coin 4 times, it will have a very limited number of values, right? Number of heads observed after 4 times. So that's it. It's either 0, 1, 2, 3, and 4. It cannot be more than that. So that's why we call the binomial variable a discrete variable. So it has a discrete probability distribution. Now the question is how to find the probability of every value of a binomial variable. The best way to do it, and because in a binomial experiment we have only 2 outcomes, that makes using the probability tree a very useful tool, or sorry, using the be very effective for us. Okay, so what do we do here? We know that in a binomial experiment we have only 2 possible outcomes, so in our tree we will have only 2 branches. One branch will represent the success and the other is a failure. Doesn't matter what do we call success and what a failure. So here's an example of 3 trials, right? So I'm showing you here, bear with me, let me get my pen here. Okay, so I'm showing you 3 trials. This is the results of the first trial, and these are the possible results of the second trial and the third trial. And I don't know about that experiment, but I know that there's either a success or a failure, and we know that the probability of a success is p, and of course the probability of the failure is 1 minus p. Then again, in the second trial, if I ended up from the first trial a success, I will also again here either see a success or a failure, and the same when we start from the failure, whether it's success or a failure, and so on, and we get these are the possible outcomes after the third trial, right? Now, to determine the probability of x successes, what does it mean x successes? Here, because we have 3 trials, so we know that if x is the number of successes, x can be either 0, 1, 2, or 3, right? Let me show you here, for example, the output of the first of these branches that starts with this S, and then it continue here, and then it reach another success and the third success. So right, remember we call that SSS, okay, which means we have 3 successes here. So here x is equal to 3, right? While here we have what? It's a outcome of a success in the first trial, a success in the second trial, and a failure in the third trial. So here x equal 2, okay? So how do we find the probability of this one? It's very easy. We learned that from previous segments. To calculate the probability of this outcome, we multiply the probability of the branches that lead to that outcome, which is p times 1 minus p, right? So this is what we do. This is what this step is telling us to do. Now, you can see in this case, I'm multiplying p twice, so this is p to the power 2, okay? And then I have 1 minus p, okay, which means it is to the power 1. And that satisfies this general notation that we have here, because I was considering the case when x is 2. So p to the power x, so that's p to the power 2 in my case, and 1 minus p to the power 1 in my case, because it's n minus x. I have 3 trials, so n is 3 minus 2, the number of successes, which is 1. So this just illustrate for you what are we doing in here. All right. Okay, so let me take out these from the way. We don't have much left, so I don't really need to take out everything. Okay, so now we know that for every one of these final outcomes, we can do exactly the same to come out with the probability of every outcome. Now we need to use something that we don't learn in this course, what's called combinatorial counting or combinatorial formula, in order to find then the final probability for the outcome that represent the same number of successes. Remember in previous example, when the salesperson was calling and he will either close his sale or not, and then when we wanted to list the number of outcomes where we have 2 sales, we had 3 of these outcomes. So the probability of 2 outcomes, of 2 sales, we added the probability up. And this is what we mean by combinatorial formula, to find then the final probability of the same number of successes, which will give us the final formula for a binomial random variable. Okay, so from the previous slides, as illustrated in the probability tree, and using the combinatorial accounting, we can then come out with the general formula for the probability of x number of successes whenever we have n number of trials in a binomial experiment. All right, so the probability that x has the value x, small x, so it can be 0, 1, 2, 3, depending on the number of trials, it's equal to n factorial, where n is the number of trials, over x factorial, x is again number of successes, times n minus x, also factorial. And here just a reminder, what does it mean in factorial? For example, 4 factorial, do you still remember that? This is equal to 4 times 3 times 2 times 1, okay, or 1, 2, 3 times 4. Then back to the formula, then times p, which is the probability of a success, which will be given to us based on historical data, for example, to the power x, where x is the number of successes, times 1 minus p to the power n minus x again. Okay. Okay, this formula is a bit complicated, but you don't need to worry, because you know that in exams you have this formula available for you in the formula sheet. So all what you need to do is to practice on how to implement it. All right, so let's do some practices.